Welcome to this class of Electrical Engineering Principles 3, DEG1305, from the School of Engineering, Energy and the Built Environment, from the Department of Electrical and Electronic Engineering. My name is Jackson Gatua. Today we are going to look at a topic in AC Series Circuits. At the AC Series Circuits, we usually have what you as the student you are expected to know by the end of this topic, and you're supposed to understand AC series networks. Also, you're supposed to be able to draw circuit diagrams, phasor diagrams, current and voltage waveforms for purely resistive, purely inductive, and purely capacitive circuits. Also, you're supposed to be able to perform calculations involving all the series circuits. Now, in the series circuits, there are components which you call passive components. Now, passive components are those components which actually limit the current in a circuit. Though they usually do this in different ways, but they usually limit the current in a circuit, and they are resistors, inductors, and capacitors. Now, these, as I have said, they limit the flow of current, but they do it in a different way, in a different manner. Now, the passive elements of these three elements, they exhaust the energy in a circuit, and therefore they cannot amplify the output, and therefore the gain of the output is always less or smaller than 1. Now, if you start with the resistors, if you look at the resistors, we know a resistor or the resistance is usually the same in both DC and AC, regardless of the amount of frequency. So frequency does not affect the value of the resistance of a resistor in a circuit. And this is because they have got some parasitic characteristic of like having zero impedance and infinite capacitance. And in a resistive circuit, current and voltage are always in phase. They move together. They are in the same line. We call them, they are in phase. If you are drawing the phasor diagram, then you get the current and the voltage, they are going to be on the same line. If it is horizontal, they are on the same line. And to get the power output in a resistive circuit, then it's given by I times V, which is where I is the current and V is the voltage. And then if you look at the inductors and capacitors, now this one have got a different kind of opposition to the flow of current, which is called reactance. We have got the capacitive reactance, and we have got capacitive reactance, and we have got inductive reactance. And for the case of these two passive elements, they usually affected by the supply frequency, unlike the resistance, whereby if the frequency changes, the value of the reactances also changes, as we are going to see later. And we have seen that the inductance and capacitance offer a different AC resistance, which is known as reactance. So you have got, as I've said, you have got capacitive and inductive reactance. Now, the reactance value of an inductor varies with the source frequency. These three passive elements are employed in the electric circuits in several configurations. So we have got series configuration. You can have the three components, maybe 3 of them or 2 of them being connected in series, or you can have them being connected in parallel, or you can have the combination of both series and parallel circuits. And therefore, for today, we'll just look at the series combination or series circuits of either of the resistor, inductance, and the capacitance. And we are going to see in all of them, we are going to assume the supply voltage is usually pure sinusoidal voltage, which is given by the formula V is equals to V subscript M sine omega t, where V is now the supply voltage given by Vm is the magnitude or the maximum of the waveform. You have said this is a sinusoidal waveform or a sine wave, whereby you have got the amplitude of that wave. So that amplitude or the peak value is our Vm. And then you have got omega t. This omega is the angular velocity, and it's given in radians per second. And we have got t is the time in seconds. So this is very important when it comes to AC, because when we talk of DC, they do not have got this kind of a component, because it's just direct. Now, if we consider a purely resistive circuit, that is a circuit which have got a resistor connected to the source. This is the source of the voltage. This is the current which is flowing through this resistor, and you have got the voltage drop across this resistor is going to be given from the Ohm's law, is going to be given by the current times the value of this resistor. Now, the phasor diagram, as I mentioned earlier, is that current and voltage across the resistor is, or they are usually in phase. They move together. There is no phase difference. That's why they have been drawn on a horizontal or the same line like this. Now, at the same time, this can also be shown by a wave form, like what we have seen here. We have got the voltage across the resistor here. We have got the voltage, the current waveform here. So as you can see, they are all starting at the same point. They are starting at point 0, moving together and crossing the x-axis together, and then they end at the same point. So this is a complete cycle. So this, we say they are in phase. The two of them are in phase. They are not leaving each other. So a purely resistive circuit have got the current and voltage in phase. Now, if we look at a pure inductive circuit, a circuit which have got an inductor in it, then you are going to have got the voltage across the inductor or the supply voltage, then the current here, and then the inductor is there. And here, we usually see something different from what we have seen in a resistive circuit. And this difference is that voltage across the inductor and the current across the inductor, they are out of phase by an angle of 90 degrees. Here we say that current is lagging behind the voltage. Now, we usually take the anticlockwise as the forward rotation of an alternator, or the forward rotation, and therefore, when we are talking of the anticlockwise rotation, then it means this VL is ahead of IL, and therefore, we take current as the reference point, and therefore we have got IL is lagging behind VL. IL lags behind VL by 90 degrees. And as you can see from this waveform here, they are not on the same line as, they are not starting at the same point as we have seen for the case of purely resistive circuit. Now, the current is starting at 0, while the voltage is starting on a positive point. Therefore, it is leading. And when they come to cross the x-axis first, you see the VL is crossing first the x-axis, then followed by the IL. The difference between them on the x-axis, this is what gives us the phase difference. So we say they're out of phase. And this is the angle that we are giving here as 90 degrees. So this is the waveform showing the current lagging behind the voltage. It's drawn like that. Now, in a purely inductive circuit, the opposition to the flow of current is called inductive reactance. Like what we said in the purely resistive circuit, the opposition to the flow of current is resistance. Now here, we have got the opposition to the flow of current is inductive reactance, which is denoted by this symbol, reactance. This is XL, X subscript L. And to get this reactance of the inductor, Then you get the voltage divided by the current, the voltage across the inductor divided by the current across that inductor, and it's going to give us the value of XL. Still, you can also get the value of XL by multiplying 2 pi FL, where 2 pi F is omega. It is angular velocity. 2 pi F is angular velocity, and simply you can also say that XL can be given by omega L, and the units is ohm because they are opposing the flow of current, therefore the units is going to be given in ohms. Now let's have an example here. Calculate the reactance of a coil of inductance 0.32 Henry when it is connected to a 50 Hertz supply. Now, it's good you do what is called question analysis. You write the components which you have or what you have been given, and then you work out what you have not been given. Here, you have been given L. The value of L is given by 0.32 Henry. We have also been given that the frequency is 50 Hertz. You have the frequency is given by 50 Hertz. And then the question is asking you to calculate the reactance of the coil. You calculate the reactance of the coil. Remember here we have said this is going to be given by VL over IL, but now we have not been given V's and I's, so we use the second part, which is going to be 2 pi F, which we said this is like omega, and then multiply by the value of the inductance, and this is going to be in ohms. And when you put the values, you are going to have 2 times pi times frequency is 50 times the inductance, which is 0.32, and when you work out this one, you are going to get the answer as 100.5 ohms. Now, we have got part B of example 1. A coil has a reactance of 124 ohms in a coil has a reactance of 124 ohms in a circuit with a supply frequency of 5 kilohertz. Determine the inductance of the coil. So again here, you have been given the values of the reactance, you have been given the values of frequency, and now you get the value of the inductance. So using the same formula, this is part A, this is part B, using the same formula, or writing down first what you have been given. You have been given the XL is equals to 124 ohms, and also you have been given frequency is equals to 50 Hertz, 5 kilohertz, 5 kilohertz. So which means it's 5 times 10 raised to power 3 Hertz. Kilo means times 10 raised to power 3. And then you're supposed to determine now the inductance. So make L the subject of the formula. So you have got XL is given by 2 pi FL. So making this L the subject of the formula, you are going to have L is going to be given by the reactance of the inductance divided by 2 pi F, and this is going to be given by 124. You have got 124 divided by 2 times pi times the frequency, which is 5 times 10 raised to power 3. So when you work this one out, you are going to get the value of the inductance as 3.95 times 10 raised to power negative 3 Henry. So this is the answer which you are going to get, which this times 10 raised to power negative 3 can also be written as milli, and therefore this can also be given by 3.95 times 3.95 milli Henry. This is 3.95 milli Henry, small m, milli Henry. This is small m. Now, that is the way you get the value of the inductance when you are given the reactance, and also the way you get the reactance when you are given the frequency and the inductance. Now, we have got the other passive component, which is a capacitor, and a purely capacitive circuits look like the way you are seeing here, and this one is a capacitor connected to a source of EMF here, which is the value of VC, or the voltage across that capacitor. We have the current moving through that capacitor. Again, in this one, you are going to see that the behavior of the current and the voltage across the capacitor, they are not in phase, but they are out of phase again with an angle of 90 degrees. And we have the current at this time is leading the voltage, because we said you are taking the anti-clockwise direction to be the forward direction, and you are going to have I is ahead of VC, and therefore this one we say current is leading the voltage. On the other figure, we have got the waveform that is going to be formed when you have the current wave and the voltage wave, and you can see the current is starting at 0.0, whereas the voltage is starting at a negative point, which means that current is ahead. If you want to know that, you check when they are crossing the x-axis, when they are coming from the positive side, current passes the x-axis at this point ahead of the voltage. So the difference between the two waveforms when they are crossing the x-axis is what gives us the phase difference, which is going to be 90 degrees. Now, the opposition to the flow of current in a purely capacitive circuit is called capacitive reactance. This is the opposition to the flow of current. It's abbreviated by X subscript C, and to get the X subscript C of this reactance, then you get the voltage across the capacitor divided by the current across that capacitor, and then this can also be given by 1 over 2 pi fc, where again this 2 pi f is the value omega, or the angular velocity, and the units is in ohms. We have got an example where we have got, you are told to determine the capacitive reactance of a capacitor of 10 microfarad when connected to a circuit of frequency 20 kilo ohms. So what you have here, what you have been given first, you have been given the frequency, which is 20 kilohertz. So this is 20 kilohertz. This is the same as having 20 times 10 raised to power 3 hertz. And then you have been given the capacitance of that capacitor, which is 10 microfarad. Capacitance is 10 microfarad. It's 10 times, it's 1 times 10 raised to power negative 6. So this is going to be 10 times 10 raised to power negative 6 farad. So we want to get the inductive, we want to get the inductive capacitive inductance, or the inductance of the reactance of the capacitor, which is going to be given by the formula which you have seen is 1 over 2 pi fc, and this is in ohms, and then when you put the values, you are going to have 1 over 2 pi times the frequency, which you have seen is 20 times 10 raised to power 3, and then we have got the capacitance is 10 times 10 raised to power negative 6. So when you work this one out, you are supposed to get an answer which is 0.796 ohms, 0.796 ohms. So when you work that one out, you are going to get that as the ohms. Now, that's the way you get the reactance of that capacitor, or the capacitive reactance when you have been given those values. Then part 2, you have been told to calculate the current taken by a 23 microfarad capacitor when connected to a 240 volts 50 hertz supply. Again, this is part A, this is part 1, this is part 2. Here you have been given the value of the capacitor as 23, so C is equals to 23 microfarad, and also you have been given the voltage, which is given by 240 volts, and the frequency is given by 50. Frequency is given as 50 hertz, and then you're supposed to get the current flowing through that capacitor. So here we just come and write the formula of finding the reactance of the capacitor, which we said it's going to be given by VC over IC. So we get the voltage across that capacitor times the divided by the current across that capacitor, and of course here you're going to come and make the I the subject formula. And here we have seen this can also be given by 1 over 2 pi FC, and this is in ohms. So first of all, you have to get the value of this reactance here. You have to get the value of this reactance here, so that you make now I the subject of the formula here. When you have it on this side, the value of this side, such that I is going to be given by VC. So let's work this one out. First of all, calculate the XC. It's going to be given by 1 over 2 pi times the frequency is 50 times the value of the capacitor is 23 times 10 raised to the power negative 6. And then when you work this one out, you are supposed to get the value of the we are going to get the value of the capacitor, this one. Okay, let us first work this one out in such a way that we make this the subject, we make I the subject of formula, which is I is going to be given by VC over reactance C, which is going to be V is 240 volts, V is 240 volts, and our reactance we have seen is going to be divided, it's going to be 1 over 2 pi times 50 times 23 times 10 is power negative 6. So this is our XC. It is this 1 over that. And then 240 divided by that, of course, it's like having 240 over 2 pi times 50 times all that. And then the answer, when you work this one out, the answer which you are going to get for the case, for the value of current is going to be given by the value of 1.73 amperes. So that's the way you get the amount of current. So first of all, you get the formula, and then you make I the subject of it, and then you work the problem out like that. Now, if we proceed, we are going to have now the second part is when you have got the resistor and the inductance being connected in series. Now, in the first diagram here, we have got the resistor, we have got the inductor, such that we have got the voltage across the resistor as VR, the voltage across the inductor as VR, and we have got the resultant voltage V. And it is important to note that unlike the DC circuits, here we do not get the arithmetic value of the two voltages. But in AC circuits, we get the phasor value of the resultant voltage, like what we usually do in vectors. You have got two vectors, and then you get the resultant, such that the voltage across the resistor R is going to be on the horizontal part, and then the vertical is going to be VL, because they are out of phase with each other at 90 degrees. They are out of phase with each other at 90 degrees, and therefore if you take this side to be on this one, if you take this side and bring it here, then you are going to form a right angled triangle, such that the value of the resultant here is going to be given by V squared, VR squared plus VL squared, which is going to give us V when you get the square root of that. That is from Pythagoras' theorem, because it is a right angled triangle. And this is just like what we have here. So the voltage across the resistor is given by IR. The voltage across the inductor is given by current times the reactance, and the resultant voltage V is given by I times Z, as we are going to see. So we have seen that V is going to be given by VR squared plus VL squared square root. So that is what we have seen from this diagram here. So if we start from that point, that our V is given by the square root of VR squared plus VL squared, then this we can rewrite it just like we have seen. The value of VR is given by current times the resistance, you square that, then plus the value of the voltage across the inductor is given by the current times the inductance, then we square that, and then you get the square root. Note that both of them current is common, so you can factor out current, and then you have current times R squared plus reactance of the inductor squared. Now, this component here, which you have found here, this component here is known as impedance. That one is known as impedance, and it is abbreviated by Z. It's called impedance, and it's abbreviated by Z, which simply means the V, the resultant V, can be given by I times Z. I times Z. And as you can see, this is what we have in this diagram here. V is given by I times Z, where Z is the impedance. Now, these values, this value which have given us this impedance here, the resistance, the reactance, now if you have now Z, it tells you that again from Pythagoras theorem, this one are going to form a right angled triangle. That right angled triangle is what we call impedance triangle, and it's what we have here. So we have got R, we have got XL, we have got Z. So to get Z, you get R squared plus XL squared, the square root. And therefore, that is what we call an impedance triangle, which is very important in our calculations. Then there is this angle which is between the voltage across the resistor and the resultant voltage, or simply the angle between R and Z. This angle is known as phi. And to get this phi, you just get the tan of phi is given by VL over VR. Of course, tan of an angle is opposite over adjacent. So it's going to be VL, which is like what you have here, VL over adjacent, which is VR, is what we have here. Still, it can be given from this side, which we have got XL over R. So tan theta can be given by XL over R, or the angle itself is going to be the tan inverse of XL over R. Now, the power in this kind of a circuit is going to be given power, as we have seen in this formula. It's given by voltage times the current times cos phi. So we have got power be given by I times V. This is I times V times cos of phi. This phi is the angle that we are talking about here. So this angle here is the one that we are talking about as phi. So the cos of this phi is the one which is used to get the value of the power when you multiply it with the voltage and the current. Now this cos phi is usually given another name, and it is called power factor. So power factor is this cos phi, and it's very important in the AC circuit. And this power factor can be defined as cos of the angle, like what you have here, and it can be leading or lagging. Can be leading or lagging depending whether the circuit is capacitive or it is inductive. We have seen we have seen that when you have got a capacitive circuit, we have got the current is lagging behind. When you have got an inductive circuit, current is leading, and therefore it can be defined from the cosine of that angle. Also, you can get the definition of the power factor from the values of the resistance and the impedance. So if you look at this diagram which you have here, the cos of this angle is given by adjacent over hypotenuse. Cos of this angle is given by adjacent over hypotenuse. So R over Z, which is resistance over reactant, resistance over impedance, is going to give us the value of the power factor here, resistance over impedance. Another way to get the power factor is getting the ratio of the powers. You have got true power over apparent power. True power is given in watts, apparent power is given in volt amperes. Of course, this is the units of short form of watts, the short form of volt amperes. So simply we can say that power factor is the ratio of true power to the apparent power. And then these powers that you are talking about, the true power, reactive power, we have got a power triangle here. Power triangle here, which gives us three types of powers. Active power. Active is also called true power or real power. We have got reactive power, and we have got apparent power. In AC systems, active or real power is the power that is actually used by the loads. It is the important power. It's the power that is used by the motors, all those devices, the actual power. And then we have got the reactive power. This is the power which is developed in the coils. It is not so much important, but it comes about as when you have got inductive loads. Because ideally, in a purely resistive circuit, we would have, in AC circuits, which does not have loads, we would just have a purely resistive circuit, whereby it is only the resistance of the conductors. But when you connect loads like motors, which are inductors or which have got which are inductive in nature, then they change the circuit. They change the circuit, and therefore we would have the reactive power, and then the apparent power being the capacity of the grid to be able to accommodate the real power and the reactive power. And therefore, in terms of formula, we usually get the apparent power, which is abbreviated by S, is calculated by the voltage times the current. So the voltage times the current, it gives us the apparent power. And the active power or real power, or it's also called true power, abbreviated by P or abbreviated by W. This one is given by the formula VI cos phi, which is the formula that we have talked about, that we get when we are solving problems of RL series circuits. So this is the real power, is the power that is actually used by the loads. Then we have got the reactive power. This power is given by IV sine theta, because it's on this side. Then if you get the sine of this one, is going to be opposite of hypotenuse, and therefore you get the formula of calculating this reactive power being given by current times the voltage times the sine of the angle, and the units is VAR or volt ampere reactive. The units of real power is watts. The units of apparent power is volt amperes. Of course, because they form a right angle triangle from Pythagoras theorem, then you can just get the value of S, which is going to be given by S squared is equals to P squared plus Q squared square root. Now, just to be able to understand a little bit on this active, reactive, and apparent power, I have a photo here which is very pleasing to some people, and you can see there is some content which is here, and this content here is the one that actually cures the dust. But again, there is something that forms when you pour this content here. There's something that forms here which you call froth or foam. It comes along when you have got this being poured here. Therefore, in terms of our powers, this real power, this is what is going to help. This is what is actually helpful. But this one comes about as a result of having this one. It's wasteful. Okay, it's reactive power. And then the apparent power is the capacity of the glass to be able to accommodate the real power and the reactive power. So this is just an explanation to show you actually what the real apparent and reactive power are. Then we have got an example here. A coil with a resistance of 4 ohms is connected in series with an inductance of 9.55 milliohms to a 240 volts, 50 hertz supply. Then you are supposed to calculate the reactance, the impedance, the current taken, the active power in the circuit. Then, again, here, it's good you have got a question analysis of the values which you have been given. And what you have been given here is that the resistance is 4 ohms. And you have got the inductance is 9.55. L is 9.55 millihenry, which is the same as having 9.55 times 10 raised to the power negative 3 Henry. And then we have got the voltage is 240 volts, and the frequency is 50 hertz. And then the first question is asking you to get the reactance. The reactance of the inductor. The reactance of the inductor, of course, is going to be given by the formula which you have said is going to be 2 pi FL. This is going to be 2 times pi times the frequency, which is 50, times the inductance, which is 9.55 times 10 raised to the power negative 3. And this is going to give you, when you work this one out, is going to give you an answer which is it's going to give you an answer which is 3 ohms. Going to give you 3 ohms. That is the reactance of the inductor. Then part B, the impedance. The impedance is abbreviated by Z. It's going to be given by R squared plus XL squared, then square root of that, which is going to be R is 4 plus now inductance is 3 squared, and then square root of that is going to give you 5. Then part C is asking you to get the current taken. So the current taken is going to be given by, remember, we have got the voltage, we have got now the impedance. So the current is going to be given by the voltage divided by the impedance. Okay? So impedance is now the total opposition to the flow of that current, and therefore this one is going to be 240 volts divided by the impedance, which is 5, and this is going to give us a value which is 48 amperes. And then we have got the last part, which is asking you to get the active power in the circuit. So active power, we have said, is calculated by P is given by I times V times cos phi. This is the formula of getting the active power. We have got the current, we have got the voltage, we don't have the cos phi, but it's very easy to calculate because you have seen cos phi can be given by R over Z. because phi is given by R over Z. Now, therefore, in our formula, we are going to put current is 48 times 240 times cos phi, we have said is 4 over 8, 4 over 5, 4 over 5. Because our R is 4, our Z is 5, R over Z. And the answer which you are going to get here is going to be 9. You are going to get 9,216 watts. Or simply, this can be written by as 9.216 kilowatts. So when in terms of thousands, then we use K to refer to 1,000, and therefore this is going to be 9.216 kilowatts. So that is the way you get the power, the true power of this kind of a problem. Of course, if you had been asked to get the reactive power, then you just get IV sine of this angle. If you had been asked to get the apparent power, it is IV only. Okay? So that is the way you go about finding the value of that power. Now, from there, we have got the RC, or the resistor and capacitor series circuits. So this is when you have got a resistor connected in series with a capacitor. Okay? So the circuit is going to be in an AC series circuit containing a capacitance C and a resistance R. The applied voltage V is in phase, is the phasor sum of VR and VC. So that just like what we had in the RL circuit, you get the resultant voltage is the phasor sum of the voltage across the resistor and the voltage across the capacitor is what gives us the total or the resultant voltage V. So the voltage across the resistor is going to be abbreviated by V subscript R, and voltage across the capacitor is going to be abbreviated by V subscript C. Of course, there is going to be an angle between them, which is shown by angle phi. Now, when you look at the connection of that kind of a circuit, here you have got the resistor, we have got the capacitor here, the voltage across the resistor, the voltage across the capacitor here. This is the resultant voltage. Just like what we had in a capacitive circuit, current usually leads the voltage, so the same is going to happen in this. So here we usually have got a leading power factor. That is from the current leading the voltage. And the angle between the two of them, current and the voltage, is going to be alpha. So this angle ranges from 0 up to 90 depending on the values of VR and VC. They are the ones which dictate the value of this angle. As you can see from this diagram here, you can see we have got the value of VR is going to be given by IL. So VR, V across the capacitor, they actually dictates the value of this angle which is given here. And of course, again, this is also the power factor angle, because as you can see from this impedance triangle here, we have got the R, we have got the reactance of the capacitor, and here we have got the impedance, which is the resultant of R squared, XC squared, and then square root of that, you get Z. And therefore, this angle is the same as that angle. Now, let's have an example here. A capacitor C is connected in series with a 40 ohm resistor. So again here, we have got a capacitor is connected in series with a 40 ohm resistor. So the resistor is 40 ohm. And then across a supply of frequency 60 hertz, The frequency is 60 hertz. A current of 3 amperes flows and the circuit impedance is 50. So you have got the current 3 amperes and you have the impedance as 50. Then we are supposed to calculate the value of capacitance C. Here you have got the capacitor, we have got the resistor, we have got the frequency, we have got the impedance, we have got the current. Then we are supposed to get the value of capacitor C. Remember the value of the capacitor, the value of the value of the capacitor is going to be given by the formula which we said that we have. XC is going to be given by 1 over 2 pi FC. So if you make C the subject of the formula here, we are going to see that this one is going to be given by, so C is going to be given by reactance C times 2 pi F. So that's how you are going to get the value of that capacitor. But now we do not have the reactance of the capacitor. We have got the frequency, it is this, 2 pi we know, but how do you get now this one? So this one, we have been given the value of the impedance is 50 ohms. The value of R is 40 ohms. From the impedance triangle, we are going to get Z is going to be given by R squared plus XC squared square root, and therefore we have got 50 is equals to 40 squared plus reactance C squared square root. Of course, you are going to get the XC is going to be given by 30 ohms. So now we have got the XC is 30 ohms. So we come and put it here. Therefore, we have got our C is going to be given by 30 times 2 pi times 60, which is our frequency. And then the answer which you are going to get there is going to be 88. You are going to have 88.42 times 10 raised to power negative 6 farads. The units of capacitance is farads. Of course, this one can be written again as 88.42 micro, which is times 10 raised to power 6 farad. So that is our part. That is our part A. That is our part A. Then part B, you are supposed to get the supply voltage. Get the supply voltage. So the supply voltage is very easy to get because we said that we have got a relationship between voltage, impedance, and current. We have got the current in our question is given. We have got the impedance is given, and therefore voltage is going to be given by the current times the impedance. Remember that? Then this one is going to be 3 times 50, which is going to be 150 volts. So this part B. And then part C is asking you to get the phase angle between the supply voltage and the current. The phase angle between the supply voltage and current is simply the angle that we were seeing in this diagram here. The voltage between this is the angle that we are talking about here. It's the same angle here, and we said it's going to be given by the tan inverse. So tan inverse of alpha is going to be given by, you can use the tan or you can use the cos. Because you have got R, value of R, you have got the value of Z, we have got the value of the reactance. But when you use this one, it's going to be XL over R, which is going to be XL. We have seen it was 30 over 40, and therefore this becomes 0.75, and of course tan inverse of 0.75 is going to be around that 6.87. That's 6.87 degrees, and this is leading. Must indicate that, to note that this is a capacitive, or it is a capacitive circuit. So that is the angle that is between the supply voltage and the current. Then the PD across the resistor. Of course, to get the voltage across the resistor, the PD across the resistor is going to be given by VC, which we have seen in the diagram is given by the current times the reactance of the capacitor. And then this is going to be given by 3 times 30, which is going to be 90 volts. It's going to be 90 volts. And then we have got the PD across the resistor. We have the PD across the resistor. Still, you can calculate the PD across the resistor. In fact, this one was asking the PD across the resistor. Again, VR is going to be calculated by I times the resistance, which is going to be 3 times. Is going to be 3 times the value of resistor, which was 40, and then this is going to be 120 volts. So this is VR, this is VC. Though VC, we had not been asked here, we had been asked about the value of the voltage across the resistor. And then you're supposed to draw the phasor diagram. Of course, the phasor diagram is going to assume what we have here. So you just come and have this. This is the phasor diagram that you're going to have, the VR, the VC, this is the V. And of course, now we put the values. Put the values here. Here we have seen it's 120 volts. Here we have seen it is 90 volts. Here, this one was the supply voltage was given as the supply voltage was given. It was not given, but you needed to calculate it so that you get the supply voltage there, which of course when you get to this diagram here, it is VC squared plus VR squared, then you get the square root, and then the value is what you put here, and then the angle here you have seen is that 6.87. The current here is we have seen the current here is 3 amperes. It is given in the question. So that is the way you are supposed to go about that problem. Then this circuit is when you have got the 3 passive components combined together in series. So we have got the resistor, we have got the inductor, we have got the capacitor connected in series, and in this circuit containing the resistance R, capacitance, inductance L, and capacitance C, the applied voltage is the phasor sum of VR, VL, and VC. Again, as we have seen the previous examples, we do not do the arithmetic sum, but what we usually do is the phasor sum. So we have got the figure in the next page, which you are going to see, and it is giving us exactly what we are talking about. So this is when you have R, L, and C connected in series. So we have got VR, VL, and VC. So to get V, you are not supposed to get the arithmetic sum of these, but you are supposed to get the phasor sum, which is given in this kind of a diagram, either this diagram or this phasor diagram. Now, we have got 3 scenarios. We have got 3 scenarios that occurs in this kind of a circuit, and that is when we have got XL being greater than XC. That is the reactance across the inductor and the reactance across the capacitor. The reactance across the inductor is greater than the reactance across the capacitor. So the impedance in such kind of a case is going to be given by R squared plus the difference between the two squared and then square root. And if you look at this diagram, this is when you have got XL being greater than XC, such that the voltage across the inductor is also greater than that one across the capacitor, and then you have got the difference is that. So this is also given by IXL. So we have seen that the resultant voltage V is going to be given by the phasor sum of VL minus VC squared plus VR squared, then square root. Just like what we have seen in the previous examples. So we have got this right angled triangle. So this side is VL minus VC. This side is VR. So you have VR squared plus this value squared, and then you get the square root for you to be able to get that. Then this is the angle that is between the voltage and the resistance. Okay? So we have it like that. When you have the value of VL or XL is greater than XC. And then, of course, the impedance triangle is going to have, again, the values of R on the horizontal, the value of the difference between the two reactances, which is on the vertical, and then the square of the two added together, and you get the square root, will give you Z. Then, the other situation is when you have the XC is greater than XL. So the reactance across the capacitor is greater than the reactance across the inductor. Therefore, the formula, what changes is only here. So here, this was one which was greater. So this is the one which is greater here. So you do the subtraction like that, and then the square is there. The square root, the square is there, and the square of R is there, and then the square root. Okay. Of course, the angle in this point and at this point is get the tan of the angle is given by the opposite of adjacent, which the opposite is the difference in the reactances. The adjacent is R. The same case with this. So the second scenario here is what is shown in the figure C, whereby we have got VC is greater than VL, and then you get this. So when VC is greater than VL, you are going to have a lagging power factor, because it means the capacitor is the one which is more. Here we had a leading power factor because the inductor is the one which is more than, the value of inductance is more than that one of the capacitance. That is in terms of reactiveness. And then the angle can also be found by tan inverse of this side over this side. Lagging power factor, leading power factor. Okay? Then here we have got a situation whereby you have got the reactance across the inductor is equals to the reactance across the capacitor. So we are going to have a situation which is called series resonance, and this is indicated in the figure D here. So this situation whereby you have got VL is equals to VC, and you are going to have a phasor diagram which looks like this. The current is always in phase with the voltage across the resistor. So from there, I would like us now we look at an example involving that. And the example that we have is requiring us to calculate, okay, the question is reading a coil of resistance 5 ohms and inductance 120 millihenry. So this is the same coil which has got a resistance and inductance in it. Okay, it's connected in series with a 100 microfarad capacitor. It's connected to a 300 volt 50 hertz supply. Then you're supposed to calculate the current flowing. So question analysis. So we have got this coil. This is our coil. It is having a resistance of 5 ohms and inductance, also having an inductance of 120 milli. So it is times 10 raised to power negative 3 Henry. Okay, and then we have the capacitor connected to it. We have got the capacitor connected to it is 100 microfarad. So it times 10 is power negative 6 farad. 100 microfarad, and then we have got the voltage is 300 volts. We have got the voltage is 300 volts, and the frequency is 50 hertz. Frequency is 50 hertz. Now it's good to draw this diagram because it's important for it to show us a clear picture of what it is about. So we have got this is the resistance, and this is the inductance. The whole of this one is the coil. So this is the coil, which has got the resistance in it, which is 5 ohms, and inductance in it, which is 120 millihenry. So this is the coil, and then we have got the capacitor here connected in series with that. Okay, so this is the voltage V, resultant voltage V. Of course, here you are going to have the voltage across the coil. Let's call it a voltage across the coil, which has got a resistor and an inductor in series. So this is going to be given from that point to that point. And then this is VC, which is given from that point to that point. And then the question is, the first question is asking us to get the current flowing. Now, the current flowing, remember we said current is given, or it's going to be given by the voltage, or times voltage, divided by the impedance. This is what gives us the current. The current is given by voltage times, voltage divided by the reactance. But now we have been given the voltage, but we have not been given the impedance here. And therefore, we go ahead and look for the impedance. Z is going to be given by R squared plus either XL minus XC or XC minus XL, both squared. But now here we do not know which is greater than which unless we calculate. So before we get this, we need to calculate the value of XL, and we see which one is greater than the other, and the XC. So the XL is going to be given by 2 pi FL, which is 2 pi times 50 times the value of L is 120 times 10 is power negative 3, which this answer is going to give you 37.7 ohms. That's 7.7 ohms. Then you get the reactance across the capacitor, which is going to be given by 1 over 2 pi FC, which is 1 over 2 pi times 50 times the capacitor, which is 100. Capacitance is 100 times 10, this power negative 6, and then this is going to give you an answer which is 31.83. 31.83 ohms. 1.83 ohms. Now, from here, we can be able to tell which one is greater than the other. Of course, this is greater than this, and therefore, our impedance here is going to be given by, of course, it is R squared plus XL minus XC squared, and then square root. So let's work that one out, or we just do it here. This one is going to be our R is 5, and then plus the difference between these two, this is 5 squared, the difference between those two is 5.87 squared, and then square root, and you're going to get that answer as 7.71 ohms. So we have got our impedance. We have got our voltage. So we can be able now to get the value of current. So the value of our current is therefore going to be given. So therefore, value of our current is going to be given by the voltage, which is 300, divided by the impedance, which you have seen is 7.71. And then this one, you are going to get the answer as 38.91 amperes. 38.91 amperes. Then we come to part B. The phase difference between the supply voltage and the current. The phase difference between the supply voltage and the current. So here, to be able to get the phase difference, we have seen that in the coil we have got the resistance, and we have got now the inductance, and from the phasor diagram which we had here, to get this angle here, we have seen that when you have got XL being greater than XC, then the formula that you are going to use is this. So you get the tan inverse of this one over this. So this is what is going to give us the angle. So part this is going to be tan alpha is going to be given by XL minus XC all over R. Okay? Such that the angle alpha is going to be given by now the tan inverse of the difference here. We saw it was supposed to give us 5.87 all over 5, and then this is going to give you an angle which is supposed to be 49.58. 49.58 degrees. So you get the tan inverse of that, and this one will be our answer to part B. Then when you look at part C, you get the voltage across the coil and the voltage across the capacitor. So the voltage across the coil, as we are going to see, this is our part C. The voltage across the coil, remember, here we have got the whole reactance of, or the whole resistance of the coil, which is given by, so the voltage across the inductor is going to be given by the current times the impedance of that coil, because in it has got a resistor and an inductor. So we are going to use this, and therefore our Z here is going to be given by R squared plus the reactance of the inductor squared square root. Okay, because they are housed together. So this is going to be 5 squared plus XL. We saw the value of XL was, the XL was 7.7. So that's 7.7 ohms squared, and then square root, and then the answer which you are going to get here is going to be, the answer which is going to get there is going to be 38.03. You are going to get 38.03. So this is the total impedance of the coil. Total impedance of the coil is 38.03 ohms, and therefore to get the voltage, we now get the current. The current which was not given, so we get the current I. So to get the current, we know the current is flowing, the current that is flowing is the same, and for us to be able to get the current, we know that we can use the current is the same in the A series circuit, and therefore we can use the current which is flowing in the whole circuit, which we have its voltage, which we have got its voltage as 300 divided by the total impedance. The total impedance was given by gave us 7.71, and we found the current in the first part. It was the current. The first part was 38.91 amperes. So this what was in the part A, and therefore to get now the voltage across the inductor is going to be 38.91 times the impedance, which is 38.03, and this is going to give you an answer which is 1480 volts. So this is going to be the voltage across the inductor. Okay, so we have done that because the inductor, the coil, the voltage across the coil. This is the coil. Sorry for that. This is the coil, not the L. It is the coil. The voltage across the coil. This is the voltage across the coil, because it is involving both resistance and the inductor. So it's like a sub-circuit in the whole of that circuit. So you are going to get that as the answer, and then the voltage across the capacitor. So here, part D, you get the voltage across the capacitor. Here, simply you get the current times the reactance across the capacitor, and this is going to be 38.91 times the reactance of the capacitor. We found it was 31.83, and the answer which you get after multiplying the 38.91 and that 1.83 is going to be, the answer is going to give you 1239 volts. 1239 volts. So that is going to be the voltage across the capacitor. And of course, if now you get, if you get the voltage, this voltage squared plus this voltage squared, and you get the square root, it's going to give you the resultant voltage V, a resultant voltage V, which is 300. So that is the way you go about finding the voltage across the capacitor. And here we have got an exercise which you need to tackle, and the question is saying a 40 microfarad capacitor is in series with a coil of resistance 8 ohms and inductance 80 millihenry, and is connected to a 200 volts 100 hertz supply. Then you're supposed to calculate the circuit impedance, the current flowing, the phase angle between the voltage and the current, the voltage across the coil, and the voltage across the capacitor. So you just apply the knowledge which you have seen in, or which you have used in the previous example, and you are going to get the answer. That brings us to the end of our first lesson in Electrical Principles 3. Thank you.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.